One of the good things about using a Fourier basis, which is a periodic basis, is that the functions are periodic. So they do a good job modeling periodic signals. A sinusoidal periodic signal with frequency nu takes this form. Note that the word sinusoidal refers to the shape. It can be a sine function or a cosine function, or a combination of both. The sine and cosine functions are actually the same. They're equal, but with a time delay. Detecting periodicity with a period p is the same as detecting periodicity with a frequency nu, where the frequency nu is 1 divided by the period, or the period is 1 divided by the frequency. So what we can do is look for Fourier components of cosine at frequency nu and sine at frequency nu. We look for activity at frequencies nu sub k, where nu sub k is one of the Fourier frequencies. It's k divided by n tau, k being an integer, by the strength of its Fourier coefficients, cosine coefficient and sine coefficient, when representing the data with a Fourier basis. Now, very positive and very negative both represent strong activity at the given frequency. And a given frequency's activity is the combination of its sine and cosine coefficients. So to get a good measure of the activity at that frequency, we take the sine and cosine coefficients and combine them, computing a strength for each frequency as the sum of the squares of the cosine and sine coefficients at those frequencies. And of course, any signal, even random noise, is going to have coefficients. Because our Fourier basis is a complete basis, it can represent any data. What strength represents a statistically significant signal rather than just the response to random noise? Well, we might be interested in what is the likely response to random noise. What do we expect the strength to be if the data are just random noise? Let's assume zero mean white noise. So the expected value of the noise is 0, it's 0 mean, and the expected value of the product is given by sigma squared, the noise variance, times the Kronecker delta, delta jk, so that it's not correlation between two different noise values. The expected value of a cosine coefficient is 0 because the expected value of the noise is 0. The expected square of the cosine coefficient is not 0, however. It is the square of the way we compute the cosine coefficient. It turns out to be this, and you can work out all the algebra and find out that the expected square of a cosine coefficient is 2 divided by n times the variance of the noise. You can get exactly the same thing for the sine coefficient. So when we take the cosine coefficient and the sine coefficient, square them and add them together, the expected intensity is going to be 4 divided by n times the variance of the noise.